Hello everyone, welcome back to my channel. My name is Cha Cha. Today I'm going to be going over chapter 3 of the Kaplan textbook for chemistry for the MCAT, bonding and chemical interactions. Once again, I am a student studying for the MCAT who majored in molecular biology and psychology, so some of the things I say may be wrong. And if you notice anything, please mention it in the comments, just because I'm going to take the test too, and I'd rather not get anything wrong that I didn't really need to. Um, see. Sorry. Bonding. So the first thing that is important to go over is the octet rule, because that's the main thing that dominates bonding for the MCAT or general chemistry as far as we really care about. The octet rule it says that atoms are stablest when their valence shell is full with 8 valence electrons, which makes sense, octet being 8. Remember, if you combine the s and the p orbital, the s can have a maximum of 2 electrons, and the p can have a maximum of 6 electrons. So it makes sense when you consider the two. If you look at, I guess, everything below row 3, sorry, period 3. Um, Parathenol, so like argon and below, um, those are all good. They only have s and p orbitals. It gets a little more tricky once you start including the d and f orbitals, but typically that's not really required on the MCAT. Um, like I said, there's some exceptions. We're more or less looking at the different L types, so the suborbitals. So hydrogen, helium, lithium, and beryllium. If you look at where they are on the periodic table, hydrogen is here. You can only have 2 valence electrons. Helium, lithium, and beryllium, which are 1s and 2s filling respectively, they don't have that p suborbital, so they are not able to have 8 valence electrons. Beryllium is a little um and then there's boron, which likes to have 6 valence electrons. And that's just a little bit more of like a niche rule that you need to remember. But you could kind of remember that boron is special just because it's the fifth element, or it's not it's also metalloid too. So metalloids are also kind of random. And the rules that I just explained that are exceptions to the octet rule, those are considered incomplete octets, so they don't require 8 electrons. It's more 6 in boron's case and 2 for the other exceptions that I stated. And like I was saying, anything past period 3, so argon and greater than argon, so including the d orbital over here, um, those are exceptions. They can have an expanded octet. So essentially that means that they can have more than 8 valence electrons. And for the transition metals over here, it kind of depends, more or less depending on their oxidation state. And another exception that isn't really related to the suborbitals, so SPD, etc., is that molecules with odd numbers of electrons, so the individual atoms can't have 8 valence electrons. So let's say you have something with, in total, what that has, um, like if you were to add nitrogen and oxygen, uh, 5 and 6. So 5 and 6 valence electrons. That's 11 valence electrons total. There's no charge on on this compound, so that means that you're going to be stuck with 11. So one of them is going to have a radical, which is unstable. Um, now I kind of want to go into the different types of bonding. So there's ionic bonding, which is the most like I guess like strongest type of bonding. So your the electronegativity is typically greater than 1.7 when like the difference I should say between the two atoms. So it's typically metals. So over here, metals and non-metals, which is typically like your P block that you'll see on the MCAT, just because they have the greatest difference in electric negativity. Remember, when you're increasing from top to bottom, you're increasing electronegativity, and left to right, you're also increasing electronegativity, since that's just how likely that atom wants to fulfill its octet by taking in another electron. So more or less like creating that octet that way. Uh-huh. Yeah. And it completely steals the electron, so you're actually creating cation and anion completely. That's why they formed this lattice structure over here, which is often seen in many solids. So it's a rigid structure which minimizes repulsion between charges. So it kind of alternates with having that cation, anion, cation, and then it switches orientation for the next row to minimize that repulsion. Instead of having like the two anions right next to each other below, like instead you'll have this cation here. If that makes sense. Yeah, and I kind of just have more drawing. I kind of like to think about like the parent metaphor that I'll use for drawings. I kind of consider this like one of your parents is like a super A plus parent, and the other is a deadbeat parent. So the one it'll give like its entire electron, its entire all to that specific atom, and the other one doesn't do anything at all. It just takes and takes and takes. Um, Covalent bonds. The electrons are shared between two atoms, typically two nonmetals, so it's not favorable to create ions. Um, it requires more energy than it's worth. There's two different types of covalent bonds. There's polar covalent, nonpolar covalent as well. There's also coordinate covalent, but that's a little different, and we'll kind of get to why. Polar covalent is when one atom has a noticeably strong attachment to the electron. So the electron spends most of its time in that atom's orbital compared to the other atom. And typically it has a difference of electronegativities of zero point 0.4, between zero point 0.4 and 1.7. Sometimes you'll see zero point 0.5, but I was always taught zero point 0.4. It's kind of arbitrary and you don't really need to know these numbers specifically for the MCAT, so don't waste your time memorizing it. Um, I kind of consider this more like weekend parents. Like, for example, like chlorine has most its electron. If you're considering like the electron, like the child, it spends most of its time with chlorine, and hydrogen has spends a little bit of time in its orbitals. Um, yeah, and there's also a dipole with this one in the bond. So the dipole points towards the partially negative atom. This kind of it's easy to remember. It kind of looks like a positive, like this end of the dipole. So that's how I remember like which direction it should go. Then there's nonpolar covalent, which is when both atoms share the valence electron equally. So typically there is a difference of less than zero point 0.4. You'll typically see this with like hydrocarbons a lot, as well as atoms that are the same. Like if you have like I2, or like one of that, like it's just same atoms that are bonded to each other, or like N2, nitrogen. Uh, then we have coordinate covalence. So, this is when both of the shared electrons only come from one atom. So it's very common in acid-base reactions, nucleophile electrophiles, etc. So over here, I kind of have this nucleophile and this proton. And proton, remember, doesn't have any electrons in its shell. It's just a proton, hence the name, for hydrogen. So the nucleophile will do its nucleophilic attack on the electrophile, and they'll kind of like share these bonds. And it's important because especially after it gives the nucleophile share gives its electrons to that proton or just like anything in the electrophile, it actually shares. It becomes like a typical either polar covalent or non-polar covalent. Typically it'll be a polar covalent bond. They share the electrons now between the two, and it just acts like any other covalent bond would. And it's important because sometimes you'll see in practice questions or just in the MCAT it says, is this type of bond an ionic coordinate bond? And it's never, there's no such thing as an ionic coordinate bond. Um, it's only covalent. And I like to think of these types of bonds as step parents because they didn't initially have the electron itself, but it's stepped up and it just acts like any other parent would. Yeah. Then I kind of want to go into properties of covalent bond. I kind of have my crude drawings over here, so apologies if it's kind of hard to make out. So single bonds are typically of a sigma orbital interaction, and sigma orbitals are the strongest interactions compared to sigma sigma is a stronger bond than a pi pi, but just because double and triple they have more of the pi orbital interactions, those are stronger. So a sigma for a double bond is a sigma orbital interaction plus a pi orbital interaction. And a triple bond is a sigma orbital interaction plus two pi orbital interactions. And that's the shortest bond length, so it's the hardest to break a triple bond, which makes sense. And I'm saying shortest bond length because just like the difference between like the center of the center of the nucleus here is smaller than it would be for a single bond. And now I kind of want to go over the list structure, but first it's kind of important to orient ourselves to the periodic table once again. So sometimes you'll see Roman numerals up above the different like columns or groups. So column one is named after for only having one valence electron, two valence electrons. The transition metals have variable oxidation states. So sometimes you'll see iron like 3 plus or iron 2 plus. Um, then you'll see for boron in row three, you'll see three valence electrons, four valence electrons. Over here, five valence electrons, six valence electrons, seven valence electrons, and eight valence electrons, respectively. Um, and when you're looking at Lewis structures, a general rule of thumb is that the least electronegative atom is central atom. So typically that is carbon just because it's more likely to like share its electrons with the other atoms that are bonded to it. Halogens and hydrogens, another thing is that they typically occupy the terminal slash end positions, so they can never become central atoms. Just because in hydrogen's case, it only has two valence electrons, remember, and halogens are just so electronegative that they don't want to share electrons with anything else that they can bond to. They are very greedy, so they want to keep as much electrons to themselves as possible. They're not likely to form other bonds. So over here, I kind of will walk through a practice problem or a practice example. So I have methanol, or CH3OH. So the first step is to count the valence electrons. And if there is a charge, make sure that you include the charges in your valence electron count. So, if you have a negative charge, then you're adding one valence electron to your total count. But if you have a positive charge or cation, then you're going to subtract one valence electron from your total count in forming your Lewis structure. So over here I have carbon. So if you scroll up, carbon has four valence electrons, hydrogen has one valence electron, typically in this will count it as one, and oxygen has six. So one carbon for like multiply one by four, so four and six. So that is a total of 14. The second step is to place the atoms and add a minimum of one bond between each of the atoms. So for each single bond, because each bond is two valence electrons that are together, that occupy that shell. Remember, because like if you have goes like that. That's essentially what it's saying, is that it contributes one electron from each atom or valence electron. So in this case, I have five. So there's one, two, three, four, five. So five bonds. So 14 minus 10. So you're left with four valence electrons that you need to kind of figure out. Then you add the lone pairs to the electrons, sorry, to the atoms that are not involved in bonding. So you do this first to the most electronegative atom, and only if there are leftover valence electrons, then you're going to add it to the most second most electronegative atom, etc., which eventually leaves the one central atom as well. So 4 minus 4 is 0. So there, we did it. That looks like a complete Lewis structure. And like I said, if there's not enough valence electrons to complete octets for all the atoms, start creating double and triple bonds. So you could do this from like bonded atoms with the least electronegative difference to the most. So like if this wasn't like nitrogen, let's say, like if you had like a different atom here that was like more electronegative, like let's say just I know this isn't a real thing, like if this is fluorine, and you had a full octet and this is nitrogen, you would choose the nitrogen to form the bonds over fluorine just because it is more less electronegative, this nitrogen, than a fluorine would be. So for example, it's you're forming these triple bond in order to complete the octets, carbon's octet, since right now this is an incomplete octet. Carbon only has four valence electrons right now. But in this case, it doesn't. Um, Another thing is formal charge. So formal charge helps us see which configuration is most likely. It sees how many electrons an atom has in its orbital in this configuration versus its natural state or neutral state when it's just a lone atom or slash element. So this equation is typical valence electrons in a non-bonded atom. So like if you go up here, that's kind of what it's saying. So like this is 4, 5, 6, 7, 8, whatever, etc. Um, and then N is the number of non-bonding electrons, so that's the lone pairs, and then minus one half of bonding, because when you're in a bond, right, so you treat informal charge, it just treats them, they don't look at electronegativity, so treats them that they spent electron spends half of its time with one of the bonded atoms and half of its time with the other bonded atom. Um, so it kind of like shares custody of the electron equally, so they're kind of co-parents. It treats it as non-polar covalent bonds. So in this case, I have just CH. Um, so carbon, remember, that has four valence electrons, minus zero because there's no lone pairs, then minus one half of eight since it has four bonded pairs, which is equal to zero. So it's happy. There is no formal charge. Quick way to see like if an atom is happy or has no formal charge is you look at how many bonds it has, relatively speaking. So carbon likes to have in row four, that's not row four, group four. I don't know, I said row. Group. These should all be group. Uh, My bad, sorry. Group 4 has likes four bonds. Nitrogen and group 5 have three bonds. Oxygen and group 6 likes two bonds, and fluorine and group 7 are halogens. They like to have one bond. It just goes in order of electronegativity, and I just kind of think of like how many valence electrons does it have to get to 8. So 4, carbon 4 goes from 4, so it needs four like bonds, I guess. Nitrogen with five, three bonds, I guess, together. Oxygen six, two, seven with one bond. That's like a quick way to sort of remember. It's just a trick. If that doesn't make sense to you, then you could just do the formula. That's just kind of a trick for myself. Um, yeah, and then another thing to talk about quickly is resonance. So it helps stabilize the molecule by diminishing formal charge and electron repulsion. Um, just because if you have one structure, then you have multiple structures, then you can kind of spread it out. Like, for example, if one has a formal charge and the other doesn't have a formal charge, you can help negate that formal charge. So instead of like having like -1 and the other has that atom has a charge of 0, it'll be like more or less like -0.5 if it spends most of its, if you consider it just completely like half of its time it's in that structure versus the other. Um, Yeah, most of the time it's the true molecular structure is something in between when you have multiple resonance structures. So dominant, when something's dominant, it'll have norm formal charge, just because you want to reduce repulsion as much as possible. If there is a charge, you want minimal separation between the two charges. So like if you have a positive and negative charge, you want to minimize the distance to have strong electrostatic interactions. And the more electronegative atom typically will have a more negative charge, and the less electronegative atom will like the more partially positive charge, or to be partially positive, which makes sense. It can handle that charge better. Um, some. other things in this chapter to go over are geometry and polarity. So the valence shell electron pair propulsion, also known as VESPER, takes into consideration electron repulsions of fluid structures with electron pairs being as far as possible to minimize repulsions. So that's going to be a common theme throughout the chemistry textbook is just always trying to minimize repulsion, electrostatic repulsion, or differences. Molecular geometry. So there's like two terms that you should look at. There's molecular geometry and electronic geometry. So molecular geometry only considers bonded pairs. So not lone pairs for its shape. It's kind of looking at like the larger picture or spatial arrangement. Whereas electronic geometry, hence its name, it's looking at all of the electrons. So where are all of the electrons? So it considers lone pairs and bonded electrons. Looking more at the finer details, whereas this is more of like shape, broader picture. Um, Here I kind of have a crude graph of like the important shapes that are on the MCAT. I have just to orient ourselves. This is more of like two groups, three groups, four groups, five and six groups that are bonded to the central atom, and this takes into consideration um when there's zero, one lone pair, two lone pairs, and three lone pairs. Sterics you could also think of like electron dense regions. Um, so for zero lone pairs and two, it's 180 degrees of the bond angle between the two atoms here, like the central atom and its peripheral atom or what's bonded to it. So it's linear because it's 180 degrees, which makes sense. Trigonal planar, trigonal tri meaning three, right? And it's planar, so it's like kind of flat. It's not in like avoiding anything, and it has a difference of 120 degrees bent, because the electrons are like not in a bond, so like they're typically just like located centrally on that central atom, so it'll have a bond angle less than 120 degrees. It's because it's more propulsive than if it were in a bonded pair. When we get to four steric groups, you have tetrahedral, and it has a difference of 109.5 degrees between its central atom, and or I guess between like the two like bonded atoms, I should say. Um, like that are to the central atom. Then you have trigonal pyramidal, not to be confused with trigonal planar. You think of trigonal pyramidal because it still has three bonded groups, but it'll have like a more of a pyramid shape because the electrons of the lone pair are kind of above it, kind of giving it more of like a tall shape, kind of like a pyramid. So it goes points up, I guess, whereas trigonal planar is more like flat. If that makes sense. I can't really draw 3D, but yeah. Um, and it has an angle less than 109.5 and bent. It has the same name just because it's bent and scientists are lazy. That will have a bond angle of severely less than 109.5, just because you have two lone pairs. When you have five sterics, you can call it trigonal bipyramidal. Bipyramidal, just bi meaning two, so it has like two extra groups. One of the angles is going to be 90 degrees, or like so it has two, I should say, two different angle types that you'll find 90 degrees and 120 degrees. Then you'll have a seesaw configuration, which is the same thing, more or less, but one of the atoms is replaced, sorry, bonded atoms is replaced with the lone pairs, and it'll, because of the higher repulsion, it'll be less than 90 degrees and less than 120 degrees, T-shaped. Same thing, the angles between the three bonded electrons, not electrons, bonded atoms will be less than 90 degrees, for all three. Um, Linear, same thing. Not same thing, but like there's three lone pairs and two atoms attached, so it's gonna be 180 degrees, or roughly, approximately, I should say. Octahedral. This one's a little strange to me why it's called octahedral, because oct I typically think of eight, but it's six in this case for some reason. Um, and it has angles between the two like atoms that are attached to the central atom of 90 degrees, that bond angle. Square, pyramidal. Um, yeah, it's just more square shaped if you were to look at it 3D, which is why it's called. So the bond angles are less than 90 degrees. And square planar is more of a plane shape than since the electrons of the central atom that have the highest repulsion can be directly opposite of one another, which minimizes its repulsion, but it gives it more of a square shape in 3D, and it's a lot less than 90 degrees between everything. Last thing I kind of want to talk about is intermolecular forces. So inter meaning between two molecules. There's also intramolecular forces, and intramolecular forces is between two different molecules. So yeah, you'll see that a lot of the times, like if you have like a solution, um like and stuff like that or just like in day-to-day life. Intermolecular forces are really important because they can impact melting, blood pressure, shape, etc. Of different molecules. And yeah, another thing to remember is that there are none in ideal gases. Ideal gases are kind of too far apart from one another to have intermolecular forces. Like you could sort of think about it like that. Also, it would kind of mess up our precious equation of PV equals nRT if you were to consider intermolecular forces, because there's a lot, it gets a lot more complicated when you add stuff like that, since gases start behaving irregularly, like you can't really predict their movement as well. Um, so I'm gonna go from strongest intermolecular force to weakest. So the strongest is hydrogen bonding. So this one, there's not actually sharing of electrons. The protons are due to having low electronegativity when they're attached to an atom that is highly electronegative. So hydrogen bonding is, I have it here, fun. So it's FO, fluorine, oxygen, nitrogen. Those are typically the atoms you'll see that'll be that have the greatest difference in electronegativity to support hydrogen bonding. And so like that difference is so great that they kind of have ionic properties. So like hydrogen will be super partially positive, and the central atom that it's attached to will be really partially negative. So they are more prone to kind of forming like that lattice structure almost in a way to finding another partially positive charge to negate itself. Since remember, atoms always want to be close to having that formal charge of zero or having a charge of zero, since that's just as stable as it can be. Um, yeah, that's kind of all I have to say. Yeah, there can be donors and acceptors too. And dipole dipole. So polar molecules orient themselves so opposite partial charges are close to one another. So this is remember it's like just negligible in the gas phase due to distance between molecules. So over here I don't have a fun molecule, but I have the next best thing, I guess. So I have hydrochloride and hydrochloride. Um remember this is partially positive. If you were to draw um a dipole, it'd look like that. Same here. Um, yeah, so it's just more or less it wants to orient itself to negate that charge again, which makes sense. And they're attracted to one another. It's a permanent dipole compared to London dispersion, also known as van der Waal forces, where all there is induced dipole, so not permanent. And all molecules have this. This is like the baseline that everything has. It's kind of like it's just like preternatural, like every single thing has this. Otherwise, we would be in big trouble for those nonpolar bonds. So this occurs because remember electrons moving throughout orbitals is like kind of random. They kind of like go from like place to place. They can go in between all of the different atoms, so it can go in one place versus the other. And once it moves from place to place, it actually carries its charge with it. Remember, because it's a charged molecule, not molecule. So it's charged, and it can move throughout the molecule. So that means that it can change. So one atom can be slightly more negative, partially negative than the other at a certain time. Um, and it's stronger when molecules are easily polarizable, so that means that the electrons can just like move easily throughout its orbitals. which is true for metals typically. That's all I wanted to say about bonding and interactions. Hopefully that made sense and I didn't ramble too much. If you have any questions, leave them in the chat and I'll try and get to it. Bye. Thank you so much for listening.